The battle is over, but one of the wounded soldiers is still moving. A termite has locked its jaws around her leg. Another raider limps behind the column, slowed by a missing limb. For an insect colony, the obvious solution seems simple. Leave the damaged worker and replace her. Yet some ants do something more expensive. They stop, they search, and carry certain casualties home. Why spend time and risk on an individual that may never work again? The answer is not necessarily compassion. It is a strange piece of battlefield logistics built by evolution from signals, physical constraints, and the value of a worker who can return to duty. The species is Megaponera analis, a termite specialist found across sub-Saharan Africa, and its workers raid termite feeding sites in organized columns. Larger workers open the protective soil, while smaller ones enter the gaps where armed termite defenders are waiting. The termites fight with powerful jaws. They can sever an ant's leg, damage an antenna, or clamp onto a worker and refuse to let go. These injuries are not freak accidents. They're a predictable cost of getting food. And predictable losses create an opportunity for natural selection. If some damaged workers can recover cheaply enough, abandoning every casualty may waste more resources than saving them. Recovery begins with a chemical signal. An injured worker releases compounds from her head, including dimethyl disulfide and dimethyl trisulfide. Experiments showed that these chemicals can trigger nestmates to investigate and carry an ant, but this is not a tiny voice shouting for help. The same gland material can make an uninjured worker attractive to rescuers. The response also depends on context. An injured ant encountered while the column is marching toward a raid may be ignored, while one after the fight is treated as a casualty. The signal provides information. The colony's current situation gives that information meaning. The compounds announce neither diagnosis nor prognosis. They act like a location marker, increasing the chance that a nestmate pauses for contact. That pause begins another test. Even then, a chemical label is not enough. When a lightly injured worker is touched by a nestmate, she folds her legs inward and becomes compact, almost like an ant pupa. This makes her easy to lift beneath the rescuer's body and transport with the returning column. In experiments, workers made to lose 5 limbs often failed to adopt this posture. They twisted, flailed, and could not be carried securely. Rescuers may investigate or attempt to pick up, then move on, so the apparent triage is not a medic calmly judging a patient's future. It is a decentralized filter. Chemical attraction starts the interaction, but the injured worker's physical response helps determine whether evacuation can actually happen. For those that can be moved, the ride matters immediately. A limping ant is slower, less stable, and more likely to become separated from the protection of the column. In a field experiment, injured or handicapped workers forced to make the return journey alone died in 32% of cases, mostly after attacks by spiders. Carried workers largely avoided that danger. Back inside the nest, clinging termites can be pulled or bitten away. Workers missing limbs can adjust their gait, recover their speed, and appear in later raids. Evacuation does not restore a lost leg. It preserves a worker that may still have useful labor left. The worker is not repaired into perfection. She is returned to usefulness. But reaching the nest only solves the visible emergency. A severed limb also opens the ant's protective cuticle, allowing microbes from the soil to enter. That turns a mechanical injury into a race against infection. Researchers exposed standardized wounds to the bacterium Pseudomonas aeruginosa. When infected workers were isolated, 93% died within 36 hours. When similarly infected workers were returned to nestmates, mortality fell to 8%. These are experimental results, not the natural survival odds of every injured ant, but they reveal the second enemy in this recovery chain. The termite creates the wound. Microbes can make it lethal later. In nature, a wound can encounter a shifting community of soil microbes, not a single laboratory strain. The chemical infection makes one danger measurable. Without social care, bacterial growth can outrun the ant's own defenses. Nestmates respond directly to that danger. Soon after an injury, they hold the damaged limb and groom the wound with their mouthpieces, sometimes for minutes. Later, infected wounds receive more attention than sterile ones during particular periods. Infection is associated with changes in the injured ant's surface chemicals, so nestmates may be reading a changing chemical profile, although the experiments have not proven that a specific scent causes the response. During some wound care interactions, a worker adds secretions from a metapleural gland on the rear of the thorax. She may use her front legs and mouthpiece to collect secretion from her own gland or lick it directly from the injured ant's gland before treating the wound. Here, the recovery chain becomes antimicrobial treatment, although the details matter. The gland secretion was applied only in the minority of observed wound care interactions. It is not correct to imagine every injured ant receiving a standardized drug. The mixture itself is chemically complex. It contains many compounds and proteins, some with known or suspected antimicrobial functions, while others remain unidentified. In laboratory tests, the secretion inhibited bacterial growth, and when researchers blocked access to these glands, infected ants were far more likely to die. The chemistry changes who survives. Grooming may clean the wound. Gland compounds can suppress dangerous microbes. Together, simple actions produce a targeted defense without requiring anyone to understand bacteria. At colony scale, those separate effects change the accounting. A worker is not valuable because the colony assigns her a moral status. She is valuable when the cost of retrieving and treating her is lower than the cost of losing her remaining work. Megaponera raids repeatedly, and recovered workers can join later raids again. A rescue signal, a transport posture, grooming behavior, and antimicrobial chemistry each reduce a different source of loss. None needs to evolve as a complete emergency service. Small advantages can accumulate until the colony operates something that resembles a recovery chain, while remaining a network of local responses shaped by selection. This logic also explains why rescue can be selective without a planner. A behavior that repeatedly saves recoverable workers can spread through colonies that retain more productive labor, while ineffective or excessively costly responses gain less. The evidence also marks clear scientific boundaries. The strongest evidence comes from one termite hunting species, often from experiments on the smaller workers that face the greatest danger. Standardized wounds and bacterial doses reveal mechanisms, but they do not recreate every injury in the wild. Chemical changes linked with infection are promising cues, not proof of diagnosis in the human sense. And the result is more interesting than a miniature human hospital. A colony can preserve damaged members because survival, recovery, and future work are connected. On this battlefield, natural selection has made abandonment only one possible answer.